An important part of the Capsim filter design package is the support for the modeling and simulation of variable precision fixed point digital filters. We will discuss the modeling of both FIR filters, Cascade form IIR filters, and very importantly the normalized lattice filters. I will also talk about the variable precision fixed point building blocks that are available in the Capsim for developing block diagrams that implement digital filters using the basic building blocks. It is very important to be able to simulate the filters that you design using floating point by implementing them using fixed point arithmetic. And in Caption we support variable precision fixed point arithmetic so that you can perform your simulations and optimize them in terms of the minimum register lengths that you need in order to implement them to meet your requirements. To start, we'll talk about FIR filters. Here we show a bandpass FIR filter frequency response, where we have the pass band and the stop bands. And what we're going to do is implement this using a block that is provided in Capsim. We will implement this in fixed point arithmetic and compare the performance between the floating point and fixed point implementations. Here we show the direct form implementation of an FIR filter. We have the tap delay line along with the weights, in this case floating point, and we perform an accumulation on all the weights multiplied by the taps from the tap delay line to form the output, and this constitutes an FIR filter. In a fixed point implementation, there are a number of issues that arise. One is, of course, we have to quantize the input, so right there we have the addition of quantization noise. The second is that we can't use infinite precision coefficients, so we have to quantize the coefficients, so that's why the coefficients in this diagram are shown with a hat, showing that they are approximations. Typically the coefficients will be represented by a certain size word length along with a number of bits associated with the fractional part. Many times the coefficients are normalized to all be less than 1, so you can represent them as a 16-bit number, for example, and with a fractional part. And you can also allocate a certain number of bits for the integer part. And in Caption we support the specification of a word length along with a number of bits for the fraction, and the remainder of the bits, for example, used for the integer part and of course sign and so forth. So right off the bat, when you implement an FIR filter using fixed point arithmetic, you will get a deviation from the ideal or floating point frequency response due to the fact that you are quantizing the coefficients. So this is a major issue, and you need to determine how many bits you are willing to allocate in order to meet the requirements of the frequency response in terms of, for example, the passband ripple and the stop band rejection. In Capsim, we have blocks to perform the multiplication, or in the case of the blocks, subroutines that perform the multiplication, we specify the floating point coefficient and the number of fractional bits and the word size, and the subroutine will produce an output. The output size will be twice the size of the input register. So if the word length here, for example, is 16 bits and the word length here is 16 bits, then you get a 32-bit result. So the fact that you multiply in fixed point does not introduce any error. All these multiplications produce, for example, in the case we were dealing with 16-bit word lengths here, they will all produce 32-bit results. The accumulator, which is a fixed point accumulator, accumulates all the results, and we're assuming that the size of the accumulator is such that we don't have overflow. All the accumulation is done in 2's complement so that you can have intermediate overflow conditions. As long as the final result is bounded, you don't produce an error, you have an accurate result. Nevertheless, we do have the capability to saturate and enable saturating in order to model accumulation with saturation. After we accumulate all the results, we have a rounding operation which takes the accumulator, whose register size may be, for example, 64 bits or 40 bits, and rounds it down to 16 bits in order to be compatible with the input. So we have a 16-bit input coming in and we have a 16-bit output coming out. Now, in the rounding stage, we introduce a round-off error, and we have to take that into consideration. Now, in the case of FIR filters, that can be modeled as a additive white noise, uniformly distributed. So in this case, we have noise due to quantization, we have noise due to round-off, and we have a deviation from the floating point or ideal frequency response due to the quantization of the coefficients. So we have a block called FIR taps, whose counterpart for the floating point is FIR taps. And this block implements a fixed point FIR filter. So in this topology here, we are generating a sine wave. We add a gain in order to map it from, for example, floating point plus or minus 1 to, for example, 4096 to represent 12 bits. This block converts a floating point to an integer, so here we have an integer input into the fixed point FIR taps. The fixed point FIR taps has parameters in order to specify the word lengths, the number of bits for the fractional part, and the number of bits for rounding and final register size after accumulation. The output is an integer. It goes to the integer to floating point block, and then we plot the impulse response on spectrum. If we had impulse, for example, as a stimulus, or in the case of a sinusoidal input, we look at the spectrum after filtering. The FIR taps block also has another output, which can be either the floating point output or the error between the fixed point and floating point. In this case, we are connecting that to a stats probe, which will measure the RMS value of the error between the fixed point and floating point implementations. You can also ignore this buffer and connect it to a sync block, for example. This is a very interesting plot. So in this case, we're looking at the floating point versus the fixed point FIR digital filter. In this case, the digital filter was implemented with 8-bit fractional part, and we see that due to fixed point operations, we have a major deviation between the fixed point implementation of the FIR filter and the floating point implementation, due to the fact that we are quantizing the FIR coefficients, the weights, with an 8-bit fraction. Obviously, if we use more bits in the fraction, we will start to approach the floating point, but there is a error floor due to the fact that we have a rounding at the end of the filtering. Here we show an interesting plot. In this case, we're using Tickle in order to script the topology that we showed above, in which case we are changing the number of bits in the fractional part for quantizing the coefficients for the FIR filter, moving from 5 bits, 8 bits, 11 bits, 14 bits, 17 bits. And here we're showing the signal to error ratio. This is the ratio between the strength of the signal here and the error over here. So we're actually measuring the RMS power over here and obtaining the ratio between the RMS power here and the error here and plotting that in dBs. As you can see, the higher the signal to error ratio, then the closer we are to the performance of an ideal filter. And as we increase the number of bits from 5 bits to 6 bits to 7 bits and 8 bits, 9 bits and so forth, we get a gradual improvement in the performance of the filter. And beyond a certain number of bits, there is marginal improvement. So using iterative simulations like this, we can actually find the operating point in which we are satisfied with the performance of the filter given a certain number of bits in order to represent the word length and fractional part. These simulations also include the fact that we're rounding at the end of the accumulator. These particular simulations are done with the frequency being 1005 Hertz, which is within the stop band of the frequency response. So if we look at the frequency response, 1000 Hertz is in this region here. And the next plot, we're looking at the, again, signal to error ratio, but in this case we're using 5005 Hertz, which is in the passband. If we look at the frequency response, the 5000 Hertz is in this region here. We see again that as we increase the number of bits for the fractional part, keeping the word length at, for example, 16 bits, or in this case actually the word length is a larger 32 bits, we see that we can improve the performance as we add more and more bits for the fractional part, and of course beyond a certain point we get no more gain. It is important to look at the performance of fixed point filters both in the stop band and the bandpass regions. So in Caption we are able to not only design FIR filters in floating point, but we are also able to simulate them with fixed point arithmetic with variable precisions, and also do iterative simulations in order to find out exactly what number of bits for the fractional part and the word length and the final round off after accumulation are appropriate in order to meet the requirements for the filter. Next we will consider the fixed point implementation of IIR filters using the Cascade form. Here we have a band stop IIR filter with very narrow transition width, so it's a higher order filter with stringent requirements on the filter design for a band stop filter. The band stop region is around, for example, 1500 Hertz, and we have an attenuation with the stop band around 20 dBs. Here we show the pole zero diagram of the band stop filter, and you'll notice that there are poles which are very close to the unit circle, so that quantization errors can potentially lead to instabilities. And of course you have the zeros on the unit circle in order to get the band stop operation at low frequencies. Here we show the implementation of a Cascade section. We have the input basically delayed, going through a tap delay line. This is a biquad. So you have the weights for the input delayed, and you have the weights for the output, which are fed back and subtracted from the inputs in this accumulator here. So we are very interested in this architecture here because in this case we accumulate all the results of the multiplications so that we don't have any round off errors after each multiplication, but we actually accumulate them so there's no errors, and we're going to only have an error after rounding off of the accumulated results. So let's go look at the fixed point implementation. So again, as we quantize the input, we introduce quantization error. We have errors due to the fact that we're quantizing the coefficients of the Cascade sections, A1, A2, and B1 and B2. Now we don't have an error when we multiply the delayed inputs with the coefficients. For example, if the word length here is 16 bits and the coefficient is 16 bits, the output would be 32 bits, and we accumulate all the 32-bit results and round at the very end after we've accumulated all the results. So that's the only point where we introduce round-off error. Now an issue with these Cascade form filters is the round-off error itself is then fed back through the feedback mechanism here and affects the performance of the filter. So in this case, the performance is affected by the round-off error after the accumulation. And again, quantization of these coefficients causes deviations from the ideal response. You can imagine that the quantization of these filter coefficients results in the displacement of the poles and zeros, and that could, of course, cause deviations from the ideal performance. So here we have a block called FIL, which implements a Cascade filter using fixed point arithmetic with variable precision, where you can specify the word lengths, the fractional part, and the round off after accumulations. And this block actually implements the fixed point Cascade sections, and you can directly map this filter to either a DSP implementation given the DSP architecture for fixed point DSP, or directly to RTL and eventually to an ASIC, or for example an FPGA. So in this case, again, we are using a sine wave as a stimulus, again passing it through a gain in order to get it to a 12-bit number. We got the floating point to integer, and the integer to floating point. This is 100% fixed point arithmetic in this block. The floating point block is also implemented using the same stimulus, and we're able to subtract the results of the floating point from the results of the fixed point and obtain the RMS error. Over here we have the RMS error of the signal itself, and through the tickle script we're able to compute the signal to error ratio and plot that as a function of the number of bits used in order to represent the cascade sections. Quantization of the cascade coefficients, both for the numerator and denominator, for the poles and zeros. So over here we're showing the results of the implementation, the fixed point implementation of the cascade form IIR filters versus the number of bits used to represent the coefficients. And we're plotting the signal to error ratio in dBs versus the number of bits. So as we see, obviously we have a complete failure at 5 bits, but we start to improve at 6 bits, 7 bits, and 8 bits, and eventually we have incremental improvement beyond 10 bits, as shown over here. So again, using the tickle script, we can script the block within a block diagram environment and calculate the signal to error in order to make sure that we meet our specifications. In many cases, the filter would be implemented in an end-to-end communication system, and using tickle script we can actually vary the parameters for the fixed point implementation of the filter in order to meet, for example, our bit error rate requirements, and hopefully come up with the least number of bits or word length sizes in order to meet the requirements, thus resulting in lower area, for example, in an ASIC implementation. Or you might have a fixed point DSP, and you can use the fixed point DSPs, for example, word lengths, in the parameters for the filter design and make sure that you meet your requirements. These results were shown for 1500 Hertz, which is in the stop band. Here is the comparison between the stop band filter frequency response performance for 6 bits versus 8 bit in the coefficients. In the case of 6 bits, we see the dash lines here, and we see that the filter behaves like a stop band filter, but of course does not meet the requirements in the transition band, and also fails in the requirements for the stop band attenuation. And of course we have an issue here with the ripple when we use 6 bits. When we go to 8 bits, which is a solid curve, we see that we somewhat meet some of the requirements for the filter in the stop band, but if you can compare this to the floating point, you can see that we still may not meet the requirements. However, it is very important to be able to look at the signal to error ratio, which is plotted here, and we see that beyond 8 bits, at 9 bits and 10 bits, we basically cannot improve the filter performance anymore due to the fact of the rounding and the, for example, after the accumulation in each microwatt section, and of course quantization of the input itself. Let's compare this result here with the actual floating point, which is shown over here, and we see that the fixed point implementation causes ripples in the pass band, and also at some points we fail to meet the requirements in terms of the attenuation of the stop band, but by increasing the number of bits and the word length we are able to meet all requirements. One very important filter structure that is provided in Caption and in the digital filter design package is the implementation of the normalized lattice digital filter. I refer you to this paper here by Gray and Markel back in 1975, in which they derived the normalized digital lattice filter structure, which has some very good attributes in terms of fixed point implementation that I'll discuss next. Without going into too much detail, basically Caption takes the design of an IIR filter requiring that the order for the numerator and denominator, that is for the poles and zeros, be equal, and derives the lattice coefficients k sub m, and then implements this structure here, which is called the normalized lattice structure. So if we look at the filter, it is constructed of m sections. So we have an order of m on the polynomials in the numerator and the denominator. We have m sections. Each section is implemented using the lattice structure, normalized lattice structure shown over here, where we have the delay and the lattice coefficients and the square root of 1 minus k sub m squared. Now we take the input, and as it goes through this lattice structure, there's also feedback. As you can see, we feed it back here, and then the outputs of the feedback are then weighted by the weights shown over here, and they are all accumulated and added up to form the output y sub n. So x sub n and y sub n in an ideal infinite precision will match the, for example, direct form or cascade form implementation of that IIR filter. But that's an ideal infinite precision. So what you need to know is that this filter implements m sections, has the same input x of n and an output y sub n as you would expect to have in a cascade form or direct form implementation of the IIR filter. Caption takes care of mapping the design of the IIR filter to the normalized lattice structure, calculating both k sub m and the weights. And also we have blocks that implement the normalized lattice structure in both fixed point and in floating point, which you can use in your simulation in order to model your digital IIR filter. Now, a key benefit of the normalized lattice filter is as follows. Due to the particular nature of the normalized lattice filter, especially the fact that we're adding additional multipliers, it turns out that in all of these sections, there is absolutely no overflow in any of the nodes in implementing the normalized lattice filter. This is very important. The normalized lattice filter does not have any overflow and maximizes the use of the dynamic range given the word length for implementing that digital filter. The only place you may have overflow is when you accumulate the results of weighting of the normalized lattice sections as shown over here, which of course you can control using appropriate scaling schemes. Going back to the cascade form filter, if we look at the cascade form filter, where here we have this section for a biquad, depending on the poles and zeros that represent this biquad section, the values of the signals within the nodes here may grow such that when you implement them with a fixed point arithmetic, you may have overflows, and that of course is a catastrophic failure. Then in order to minimize the chances of overflow, you have to scale the inputs, for example, and that means that just because a certain section may have an overflow, for example, you scale the data such that you don't have an overflow there, but then you reduce the dynamic range in all the following sections and add more round-off noise in your implementation. Whereas in the case of the normalized lattice filter, you never have overflow in any of the nodes, and you're using the maximum dynamic range within the computations. So it turns out that, especially when you want to implement IIR filters, especially elliptic filters, with very tight constraints in terms of not only the transition but also the stop band attenuation, the best filter structure to use is the normalized lattice filters, which are fully supported in Caption, and the whole design has been automated. We also provide source code for the implementation of the normalized lattice filter both in floating point and fixed point arithmetic. The penalty you pay for is the extra multiplications shown over here, but the payoff is tremendous, and with current technology these days, the extra multiplications don't seem to be an issue. So we highly recommend to use the normalized lattice filter, especially for filters that have tight constraints in the transition and also in the stop band requirements. Let's take a look at an implementation. Here we show the spectrum of a elliptic filter which is a bandpass filter, very narrow, with very sharp transitions and a large stop band attenuation. This is the actual floating point frequency response. This is the impulse response, so you see the high resonance due to the fact that we have a very narrow band and sharp transitions here. And the impulse response, as you can see, can last for a long time. Here is the comparison between the fixed point and floating point implementation of the normalized lattice filter. In this case, we're using 10 bits for the coefficients. So for example, we can use 12-bit word lengths, and we can see that we match the floating point very well, and we meet our stop band requirements in this case. I'd like to point out that even with floating point in direct form, sometimes it will fail with this filter with floating point implementation of the direct form and even cascade form, but the filter will still operate correctly if implemented with the normalized lattice filter. In cases where the normalized lattice filter meets the requirements, using 32-bit floating point we fail, and we have to actually implement it with double precision floating point and cascade form IIR filters, but we can still implement the filter with fixed point arithmetic with a normalized lattice structure. So this is a key benefit of Caption, that it provides the design of the normalized lattice filter, including the source code for implementing the normalized lattice filter in the cases where we have the same order for the poles and zeros, and this is particularly the case in designing elliptic IIR filters. The next topic we want to discuss is the availability of variable precision fixed point building blocks in Caption. So here we show 3 of those blocks. The first block we show is the fixed point gain, in which case we have an input with a word length, for example 16 bits in this case, and we have coefficients that we're going to multiply the input by. The coefficients themselves have to be quantized, and they have a word length, in this case 16 bits, and they also have a parameter called qubits, which represents the fractional part for the fixed point implementation and quantization, of course, of the coefficients. So the parameters to the fx gain block are as follows. One is you give it the floating point gain, the number of bits for the fractional part, and the total word length. So for example, here we're using a size of 16 bits. The fractional part could be, for example, 5 bits, 8 bits, or for example 14 bits. When you multiply the 16-bit integer numbers, then you get a 32-bit result here. Now, since in Caption we can implement variable size fixed point arithmetic, the size here can actually be 32-bit, and the output would then be 64-bit. And this is the case where you can actually model different arithmetic units. So for example, if you are trying to look at the performance of your filter with, for example, a DSP that supports 16-bit arithmetic with 40-bit accumulation, for example, the TMS320 comes to mind, or you might have implementations where you have 32-bit word sizes and 64-bit accumulations, or anything in between. So Caption supports what you call a double precision integers, which represent integers beyond 32 bits, and especially model accumulation. And of course the size can be 16-bit, could be 8-bit, could be all the way up to 32 bits for the individual registers here. So this is a very important block called fx gain. We also have fx delay, which basically delays its inputs, and in the case of fx delay we're expecting integers, 32-bit integers, but those 32-bit integers could be associated with 16-bit numbers, 8-bit numbers, up to 32 bits. The next important block is the fx add, which implements an accumulator. So its input buffers are double precision integers because they are the results of the operation of the fx gain, which potentially can multiply two 32-bit numbers and get 64-bit numbers out, and therefore we actually implement the buffers using double precision integers. Even if we were implementing an 8x8 multiplication with a 16-bit result, we still use double precision to represent that. And usually in a good implementation of fixed point arithmetic, we would accumulate all the results and round off the final result, and we would use 2's complement arithmetic such that you can have intermediate overflows. As long as your output is bounded, your result would be okay, and you finally round off the result to obtain a certain register size. At the output, this register size can be anywhere, like for example 40 bits or 16 bits. Typically it's the same size as the register size used for the input. So the parameters for FXAdd are the word length of inputs prior to multiplication, which in this case are 16 bits, the number of round-off bits, which typically matches the number of bits that were used to represent the fractional part of the coefficients, the final word length, and a saturation flag. If you turn on the saturation flag, the results of the accumulation will actually be saturated based on the specification of the final word length. Here we show the implementation of a fixed point FIR filter. Here we have FX node, which takes its integer input and forks it to its output, so the outputs are exactly equivalent to its inputs. And here we're forming the tap delay line using FX delay. And here we're also showing the use of auto fan out. Here we have the tap delay line. From every tap delay line we take out the signal and multiply it times the gain using FX gain again. And FX gain has a parameter which is the weight for this particular tap. The same for the other taps, and we take the outputs of the gains and add them to each other using the fixed point accumulator here. And notice that we also take the input x of 0 and weight it and add them with the others, and we do a final round off in order to obtain the final result. So this block diagram basically implements this structure over here, where we're multiplying the tap delay line by the weights and accumulating and doing a final round off. So you can actually build up IIR and FIR digital filters using the basic building blocks here and specify parameters in order to design fixed point filters and simulate them within the Caption block diagram environment to make sure that you meet your requirements in terms of signal to noise ratio, bit error rate, or whatever your figure of merit is for your particular design. Here we show the subroutines that are available in order to implement variable size fixed point arithmetic. I won't go into too much detail here except to say that we have some auxiliary routines that are very important. For example, the fx underscore part routine, which takes a 32-bit integer as input and depending on the specification of the size breaks that up into multiple parts, and these are used in the actual variable precision multiplication in order to do the modeling for a variable precision multiply with register sizes, for example, from 8 by 8, 16 by 16 to 32 by 32 type multiplications. Here we have the routine fx add variable, which does the accumulation, and we have the round off routine, which rounds off the result of the accumulation to the specified final word length. And notice that within all these routines we have the parameter called size, which is the word length of the original registers that are input to the multiplier, and that has to also be passed through the accumulator and also to the final round off routine. The source code for the implementation of the fixed point FIR filter and the source code for the implementation of the Cascade form IIR filter are all provided with Caption, as is the source code for the Normalized Lattice filter, both floating point and fixed point. We note that in many cases the architecture of the filter has to be changed in order to support high-speed operation. For example, in the case of FIR filters, you have to do a retiming and change the architecture in order to be able to operate at very high clock speeds. In these cases, the particular architecture can be modeled using the fixed point routines shown over here, and you can use the existing source code for the, for example, Cascade form and direct form filters in order to model the architecture of your particular FIR or IIR filter that meets the requirements for your higher clock speeds. And of course, in order to do this, you need to have available the full version of Caption that allows you to develop and incorporate your own custom blocks into Caption.